Hello, BC Calculus students. This is Mr. Johnson, and I hope you're all doing well. This is section 1.7 in our course here and our last section in chapter 1, and it's on Introduction to Parametrics. If you had honors pre-calculus, have seen parametrics before. However, what I find most often is that, especially at the beginning of the year when things are a little bit confusing and fast after a longer summer, especially given the circumstances at the end of last year and the start of this year. This concept is typically one that is pretty fuzzy for students, and most people kind of struggle to grab onto it right away. We're not going to do any calculus right now with it. We're not going to do any rates of change or anything like that. No derivatives, no integration. We'll get to all that stuff in chapters 3 and 4. But what we're going to do is we're going to talk about the idea of parametrics, and it really is quite interesting, and the connection to AB calculus. So let's first talk about the connection to AB calculus. In AB, we would use particle motion in the type of context where you were either moving along a horizontal line or along a vertical line, but not both. So let's say that you had some particle that was on a horizontal line. It can move left, it can move right, but it could not move up or down. If you were on a vertical line, well, then of course it could move up or down, but it couldn't move left or right. So you were sort of stuck in a relatively boring pattern. With parametrics, what we're able to do now is add in a third parameter, and that third parameter is t, which is going to represent time, and it allows us to move all over the plane. If you end up taking multivariable calculus with me next year, if you're not a senior, we end up then moving into space. So we just kind of keep on adding elements to this. So we're going from AB calculus, which is just motion along a line. Then we're coming to BC calculus, a motion on a plane. Then you go to multivariable calculus, and it's motion in space. So let's say that we just have, I'm just going to give you the general idea here. Let's say you have a plane and you have some sort of path along that plane. And that path would not need to represent a traditional function in a Cartesian sense. It wouldn't have to pass the vertical line test, which is part of the benefit of parametrics. And let's say that you had some particle on that path and it was just moving along the path in a particular motion, okay? When that particle stops, you can take a look at that location of the particle by accessing an x coordinate based on time and a y coordinate based on time. Now, one of the confusing things that a lot of people struggle with is that you do not graph time. Time is the input in both the x equation and the y equation that allows you to access the point on the plane itself. So time is not something that we're graphing here, but it allows us to graph the motion of the actual particle. All right, let's try some examples because I think this will maybe just help by looking at some of these. Now, in your calculator, you do have a parametric mode. So if you go to your mode button, you are probably in function mode as we speak, but you could move over to the parametric mode. What I'm going to try to do, because it's really quite impossible in this explain everything context, is I'm going to try to make a separate video walking you through how to use your calculator to analyze these. It's helpful and sort of entertaining to do it on the calculator. I think that a couple of the problems, it just shows you what's happening because there is motion associated with it. The downside is that it can sometimes complicate things when we get into the calculus side of things. So what I would say is, for the most part, when you're on the calculus exam, you're going to be using function mode for everything. That includes parametrics. When we study polars, that's going to be the same thing with polars. You want to probably stay in function mode, even though your calculator can go into parametric and polar mode. But I do really want you to be well versed with calculator. I want you to be able to use parametric mode if it's helpful. And so that's why I do want to show you that. I'm going to try to make a separate video that has just the calculator on it. Okay. All right, here's example 1. So we have x is equal to t squared and y is equal to t plus 2. And we're going to graph it. And we're going to let t go from -3 to 3, and then we'll analyze what's going on here. So let me pause the video. I'm going to make a table, and I'll show you kind of what the table will look like here, where we're just going to fill in x's and y's. So let me pause. I'll come right back to this. Okay, so I have the table filled out, and now what we're going to do is we're going to sketch this. And so we have our y-axis and our x-axis. And let's see, we need 1, 2, 3, 4, 5 on the y. And we can go down to -2 maybe. And then 1, 2, 3, 4, 5, 6, 7, 8. Oh, I just lost track. 6, 7, 8, 9. And that should be fine, but we'll go to 10. Okay, so let's plot these points. Now keep in mind that the parameter that's t is allowing us to now access the ordered pair. So for instance, when t is -3, my ordered pair is 9, -1. So my ordered pair is here. Again, this is when t is -3. I'm not graphing -3, I'm graphing 9, -1. Then I have t is -2, my ordered pair is 4, 0, 1, 1, 0, 2, 1, 3, 4, 4, and 9, 5. So about right there. And again, keep in mind that t is allowing us to track where these points come from. So if we were to assume a smooth curve here, we would have some sort of curve that kind of looks like this. And not only that, but we actually have a motion to the curve based on our t-values. So our t-values allowed us to analyze how, if a particle was riding on this curve, how the particle was moving along the curve because of t going from -3 to -2 to -1 and so on. Okay, so again, this point, I'm just going to label just a couple of these just so you have the idea. This is when t is -3. This one here would be when t is 2. And you could kind of just fill in the rest. That's the idea behind what t is providing us, but we're not graphing t at all. Okay, so what's the domain? Well, first of all, let's just organize t. So t is going to be from -3 to 3, which is what we were told. The domain, so the x values, are from 0 to 9, and the range is from -1 to 5. Okay, and obviously we could expand this, but based on the problem, that's what we're given. Okay, now what we're going to do, and this is going to be a little bit strange, but you'll see that it's actually really easy algebraically, is we're going to eliminate the parameter. And what that means is that right now we have three parameters. We have x, y, and t. So I have x equal to t squared, y equal to t plus 2. So I have three parameters. I want to get down to 2. I want to eliminate one of them. And what I'm going to do is I'm going to eliminate t so I can put it into a Cartesian equation, and we can sort of think about it how we're more used to thinking about it in terms of x and y. So the first thing I'll do is I'm going to subtract 2 and solve for t in the second equation we have here. And then I'm going to substitute that in for this t here in the equation with x and t. And what we get is x equal to y minus 2 squared. Now, some of you may be able to graph that. If you can, that's excellent, and you have a real good sense of how to graph equations that are not functions. But what I'm going to do is I'm going to move it into more of a form that we're used to. Okay, so I'm going to take the square root of both sides, and in this case, we have a situation where we're taking the square root of a square. So we have the absolute value of x, which turns into plus or minus x equal to y minus 2. And I'm going to solve for y because, again, we're so used to that form. So I have y equals 2 plus or minus the square root of x. This is a sign that it is not a function originally. When we were to analyze the first equation right here, that is not a function. And we can see that because when we solve for y, we actually get two separate equations. All right, let's go back up to our picture, which is not terribly perfect, but I think it'll be helpful to see this. If you were to think back in algebra, higher algebra, if you were to graph, for instance, y equals 2 plus square root x, well, we would take the square root function and we would move it up 2 units, and guess what? We get this portion of the graph. Okay, if we took y is equal to 2 minus square root x, we would take the square root function, reflect it over the x-axis, and then move it up 2 units, and guess what? We get the other half. So if we were to graph these two Cartesian equations, we would get that green graph above. Now the only piece of this we wouldn't have is the motion. And the motion comes from what t is giving us. In this case, obviously, if we have the Cartesian equation, we don't have that parameter t, which means that we would have no idea what the motion would be in this particular. It would not have any kind of motion. Now, based on the problem as a whole, all of this is still connected, okay? So if we were to look at the Cartesian equations, which I have right here, the domain, the x values, would still be 0 to 9, and the range would still be -1 to 5. And the reason for that is that everything that I'm doing right now is coming from the parametric equations we had originally. And so the domain does not change. Even though the blue Cartesian equations have a different domain and range in the context of algebra and higher algebra, like if we were to look at that all alone by itself, I understand that. But what we're doing is we're taking these parametric equations we have in the original problem, and we are sort of analyzing them in a different way and looking at eliminating the parameter, but this domain and range is still completely connected to what's happening in the original because that's where it came from. Okay, we're going to move on to the next page and try another one. All right, here we have example 2, a little bit of trigonometry, which is definitely one of the more important functions that is used on the AP exam. In this case, the question asks us for x squared plus y squared, and this goes back to some pre-calculus that hopefully you remember. So if x is sine of t and y is cosine of t, then you have sine squared of t plus cosine squared of t, and I hope that you remember that that's equal to 1. It's one of your Pythagorean identities. And so in this case, what do you think of in terms of a graph? I hope that you're thinking of a circle. And so I'm just going to draw out a table really quickly and show you that we do in fact get a circle when we were to graph this. I'm going to set up the table really quickly, and then I'll pause, and you can try this on your own. If trigonometry is something that's a little bit fuzzy for you, as you have not done some math maybe for a little while, please try, please pause it with me and try this. But here are the values I'm going to use. I'm going to use a bunch of them because I want you to see the smooth curve here. So I want to do basically every quarter of pi here. All right, so I'm going to pause and fill out the rest. All right, so here's my table. And again, I'm going to try to produce a short video that will show you how to do all this on your calculator. It's kind of neat to watch it graph and to set up different windows and stuff, and I'll hopefully demonstrate that for you. If we were together in classroom where I had a calculator screen in front of you, I'd show you all sorts of neat stuff with that. But in this case, what I'm going to do is I'm going to start graphing some of these. Now, we're just going to sort of ballpark this, but what we're doing is starting at 0, 1, because remember, when we're looking at this middle column right here, those are all x values, and then my column to the right is all y values. So my first ordered pair is simply 0 for x and 1 for y. So I have this point here. I'm just kind of ballparking. I'm changing the scale in terms of the grid, which is fine. The next point is going to be 1 over root 2, 1 over root 2, which I'm just going to sort of ballpark as maybe here-ish. The next point, and I'll highlight this, the next point is this third one, which is when x is 1 and y is 0. So that's going to be about there. Then I have x is 1 over root 2 and y is -1 over root 2, which that's maybe about right here. And then we have 0, -1, so we're here. And then negative root 2 over root 2, you probably are starting to see a circular pattern here, and you fill in the rest. So there you go. So this was our starting value. And if you noticed, as you traveled around, this was the path of the particle. Okay, and then we did the table from 0 to 2 pi, and we were given that domain in the original here. And so what we've done is we've completed a full circle. We've come back to the starting point, and that's the path of our particle, which is kind of neat. Now in example 2, the difference is, well, we have switched the x and the y. So x is now associated with cosine, and y is now associated with sine, but we've also taken the inside of this trig function, made it 2t rather than just t. So I'd like you to think for a second, how is that going to impact things? Is x squared plus y squared still going to equal 1? Or in other words, if we were to go back up to example 1, the radius is 1 for this circle. So I guess the question is, for example 2, is the radius still 1? The answer to that is yes. So the 2t does not affect the radius. So what would it affect? What do you think would change? Let's go ahead and draw out a little table here just to get a good sense of this. And I think what I'm going to do is pause, and then I'll put just a couple values out, and then we'll go from there. Okay, so I've just done a partial table here, and I want you just to see the patterns that are forming. So we're starting here at 1, 0, which, okay, what's the reason for that? We started at 0, 1 before. Well, we've changed which trig function is associated with which variable. So x is associated with cosine, and y is associated with sine. And so that's the reason for that. That's not really a huge deal. That should make some sense that we've just changed, how they're connected. So we're starting at 1, 0. The next point is going to be 0, 1. So x is 0, y is 1. Now, we know that this is a circle just based on the trig relationship. However, there wasn't a point in between. I'm using the exact same set of data from example 1. So I'm not doing less data points, I'm doing the exact same intervals, but all of a sudden we just skipped this region in between. We know that there's not a straight line here just because of, again, like I said, we can analyze this and we know it's going to look like a circle with a radius of 1. So our brains, our intuitions can sort of fill in the fact that that's going to be a circular motion there. The next point's -1, 0, which is here. Then we have 0, -1, which is here, and we're back to the original. So in other words, we have a circle that looks like this. The starting point was here, and we moved in this type of direction. Now here's the deal. The domain is 0 to 2 pi, and we have only done half of that in our table. If we were to go all the way out to 2 pi down here, we would actually go around this circle a second time. Okay, so let me go back to the question that I was asking you. Compared to example 1, we went around exactly 1 time, and all of a sudden in example 2, we're going around twice. Does that make sense with the fact that we have this 2t inside the trig function? And hopefully it does make sense, because think about it transformationally. The 2t, the 2 is a horizontal shrink. So what's happening is that instead of going with cosine between 0 and 2 pi being one period of time, or one period on the cosine graph, or one period on the sine graph, now since we are shrinking it by a factor of 2, in between our domain, in between 0 and 2 pi, we actually have 2 periods. And that's what causes this particular graph to cycle around one more time. Now, as you draw that, that's really difficult to draw, because all you're doing is you're traveling. I'm going to do it in blue. I'm going to do it with my highlighter here. So you're traveling around this, and then you're going back around, and then you're stopping. Well, it's hard to kind of portray that if you sketch it. On your calculator, it's really cool because you can actually do it. So again, I'm going to try to show you that, but for the time being, just trust me, and I hope example 2 makes some sense. Okay, let's move on to the next page. All right, here we are in example 3. And we have x equal to sine of t and y equals sine squared t. And so I'm not going to do anything on the calculator here. What I'm going to do is first sketch this thing, using a little table. So I'm going to pause. I'll be right back. All right, so here's a little table. We obviously could put in all sorts of pieces of data here. I just chose a few just to get to 2 pi a little bit more quickly. It's going to look a little strange though. So what we have is 0, 0 as a start. Then we have 1, 1. Then we're back to 0, 0. Then we're at negative 1, 1. Then we're back to 0, 0. So a very bizarre pattern. It's almost like this is our starting point, by the way. And we shoot over here, we come back, we shoot over here, and then we come back. So it's this really strange kind of pattern. And then we go like that, and then like that, and then we come back. So it's this very kind of strange behavior. Okay, so let's eliminate the parameter and see if that will allow us to get a better sense of what's going on. So what I'm going to do in terms of eliminating the parameters, I'm going to first just write this out. So we have sine of t equal to x, and y is equal to sine of t squared. Now if you look at this for a second, take out the sine of t in the equation for y and substitute in x, and you get y equals x squared. Seems so simple it's difficult, I think. So again, what we're doing is we're taking the sine of t out of y, of the equation for y, we're taking that out, and look at what's equal to sine of t. It's x, so we're putting x in. And so what we get is a parabola, and guess what? That's about the shape we got, wasn't it? There's this little parabolic pattern right here, okay? And we would have no idea necessarily that it's curved unless we did more data here and graphed more data, or if we were able to actually eliminate the parameter here. Now, keep in mind, and I'm going to go back up to the original, our t value is between 0 and 2 pi. Now let's think about our parametrics here for a minute. So what is the domain? Now remember, x is equal to sine of t. So with sine of t, what is the minimum and maximum sine of t is on the interval from 0 to 2 pi? And hopefully you're thinking negative 1 to 1. With the range, okay, the range is my y values. So if I'm looking at sine squared t on the interval 0 to 2 pi, my minimum is 0 and my maximum is 1. And this domain and range is true for my parametric equations, but remember it's also true for the Cartesian function. It does not change because the Cartesian function of y equals x squared right here, that function came from the parametric form. So in this problem, in the context of this problem, my domain and range for y equals x squared is negative 1 to 1 for the domain and 0 to 1 for the range. Okay, let's try our last example. Now this one I would love to have a calculator to show you because this particular graph is not a function, and therefore you can't type it into a TI-84. You could type it into Desmos, and Desmos would handle it just fine. But you could actually factor this and get a little bit of a sense of what's going on, but it's not a natural equation to factor, I don't think. This gives us y squared and then the quantity y plus root 3 and y minus root 3. So in other words, x is 0 when y is 0, and negative root 3 and positive root 3. And I'm just guessing on a scale, okay? Now, if you were to think of this, and we're so used to this when it comes to an equation where it's y equals something or other, but when it's x equals something or other, we forget kind of how to react to it because our independent variable is just different than we're used to. But keep in mind that, you know, if you pretend like the x's were y's and the y's were x's for a moment, this is a 4th degree polynomial. Yes, it's sideways because it's x equals our values of y, but the same kind of behavior applies. So in other words, when we're looking at these two factors, those two factors are single degree factors while this is a double degree factor. And Some of you are going to be able to get to this point where you're able to sort of think through this particular graph, not function, and you're able to come up with a graph that's sort of similar to that. Others of you won't, and that's okay. We don't need to worry about that right now. I'm just showing you sort of an example of how you could maybe get there without using parametrics and your graphing calculator. But either way, if you were to graph this particular equation, you get something like that. Now what we're going to do is change this into parametric form, and here's a super easy way to do it. I'm going to let y equal t. Now, could I let y equal something else? Of course. I'm picking a really easy one so that we have less to worry about and less to type in ultimately. You could pick all sorts of things and you would be okay, and you could pick all sorts of things and have lots of trouble. So this would be x if y was t. And again, think about what this means. All you're doing is taking t out and putting y back in, and you have the original. So if you were in your parametric mode in your calculator, you could type this in, and you could actually graph this particular parametric function on your calculator. So on my calculator, what I did was I let t go from -5 to 5, and I let x go from -10 to 10, and y go from -10 to 10. And you could certainly pick other windows as well, but what this does is it gives you a really nice path of this particular particle where if you were to graph this and kind of slow it down a little bit, you'd see the path, start over in this area and then kind of come through and sweep through this general pattern, and that would be our particular path for this particle if it was a parametric equation. But again, what does a parametric equation do? It allows you to graph some things that are not functions, and it allows you to graph them really easily versus having to kind of go through the points and try to guess where the particular graph is going to flow. So again, that's parametrics. We will do all the calculus in not too long, but for right now, that's just a little review. And for some of you, that's a bit new. And now we can move on ultimately to chapter 2 in not too long. So thank you and have a great day.